Alright guys, so this is Connor and today I'm going to go through the Unit 7 summative FRQ. So, okay, without further ado, let's just get started. Problem 1, find the interval of convergence for the series below and show all steps. So, to find the interval of convergence over here, you want to use the ratio test, right? Because you have a power of n here and a power of n here. So using the ratio test would mean that they cancel out really easily. And the ratio test simply states that if the limit as n approaches infinity of n plus 1 over an, if this limit is smaller than 1, right, the magnitude of this limit is smaller than 1, then the series is going to converge. So this is what I basically did here, right? After I took the limit, after a series of simplifications, I got that this limit was equal to x minus 3 over 5. And then for this to satisfy our condition, this has to be smaller than or maybe even equal to 1. So this gives us that x is somewhere in between -2 and 8. It's somewhere in between this range. But the problem with this range is that we would need to test the endpoints. We need to test, does x work at -2? Does x work at 8? We need to test those two endpoints. And how do we do that? Well, when we test the endpoint, that we use different convergence tests to do that. So when x is equal to -2, this just becomes an alternating harmonic series. So you just use the alternating series test, right? Because on the top we have -5 to the n, and on the bottom we have 5 to the n, and we multiply this by 1 over n. So this just gives us an alternating harmonic series. And then when x is 8, we get the harmonic series, the sum of 1 plus n. And so this diverges by our p-test, or p-series test. Yeah, that's just question number 1. Question 2 is a tricky one, right? A lot of people missed it. And yeah, I think Willow went through it over class, so I'm just going to go through it again. So 2a, we use the integral test to show that the series converges. So what does the integral test say? Integral test basically says that, right, what do we do when we're adding up a bunch of a series, right? Basically what we're doing is we're adding up a bunch of dots together. We're adding up these y values together. But if we add up these y values together, right, we add up these small rectangles together, this kind of looks like adding up this area together. So the integral test says that if we can add up this part of the area, then we can also add up the discrete set of dots. We can add both of them together interchangeably, if that makes sense. So we would want to integrate this expression. We want to integrate that expression. And how do we do that? We can do it through a u sub. We let u equals ln n, and then we have du equals 1 over n dn. And so after using u sub, right, this becomes our u, and then 1 over n dn, this part is just equal to du. So all we get is 1 over u squared du, and then this is just a power rule. We get -1 over u. But once we substitute u for ln n, we can solve for the integral. And yeah, and one thing I want to highlight is this notation, right? So in here, we're evaluating -1 over ln n when n equals 2 and when n equals infinity, but we can't plug in infinity. We can't say equals infinity. So you have to say we plug in some t such that t approaches infinity. And then after calculating, this part becomes 0, and 1 over ln 2 stays as 1 over ln 2. So the integral is just 1 over ln 2. And what does this show? Because 1 over ln 2 is a finite value, this is finite, we can say that because our function is positive, decreasing, and continuous, the integral test shows convergence. Remember these three conditions, right? The integral test only works if the function is positive, decreasing, and continuous. And then there's the lower bound and upper bound question. So for this, my suggestion is always to kind of draw a graph. What happened? Sorry, give me 1 second. Okay, yeah, now it's good. My suggestion is to always draw a graph, because geometry first, right? So for this question, if we were to draw a graph, I'll just draw it down here, so it's a little bit easier. So we can visualize, right, each of the points. Let's say this point is when n equals 2, this point when n equals 3, this point when n equals 4, n equals 5. And then if we were to create a function, a continuous function, it would look something like this. But then, so the true area, the integral, would be this part. But then what would the sum of our series be? Well, it would be this y value over this part over this part over this part over. So our actual sum ends up being greater than the integral, and I'll just say fx here, between 2 and infinity. But we know that this integral is 1 over ln 2. So we have found that the lower bound of this sum is 1 over ln 2. All right, amazing. What about the upper bound? So again, we have these discrete dots, right? And again, we assume that this starts at n equals 2. So instead of taking this value and moving it and creating a rectangle to the right, now we instead want to create it to the left. So we want to do this, this, this. And then note that the integral from 2 to infinity is this part, right? And I'll just, on my iPad, I'm writing this part is equal to blue. So how does that help us find the total value of the whole series? Well, the whole series has to be smaller than the blue area, right? I'm actually going to call that L. This integral plus this little bit right here. And what is this little bit right here? This little bit is this when n is equal to 2. Or in other words, it's our first term. And this, again, has to be greater than the sum. Let me say that again. The integral, this part, is greater than the discrete sum from 3 to infinity. And so the integral plus the red section has to be greater than the discrete sum. And what is the integral plus the red section? The integral plus the red section is just 1 over ln 2 plus, what's the other part? 1 over 2 times ln 2 squared. And this is just coming from this, right? All right, amazing. Now, time for question number 3. So again, question number 3 is just telescoping series. So basically, just it's the work here. And I skipped some steps, but after you get here, what you want to do is you want to do partial fraction decomposition, right? So you would want to do, so this would separate to a plus n over 2 plus b over n plus 1, and use partial fraction decomposition, ultimately getting that, what, b equals 1 and a equals -1. Right? But I'm not going to show this process because I'm sure you guys are familiar with it. All right. Question 4. Derive the formula for a sum of finite geometric series. And for question 3, I'm sure Wolo talked about in class, so I'm not going to go that deep onto it. But one thing I want to notice is that all the terms cancel. That's why it's a telescoping series. Okay, question 4. So for question 4, right, sometimes it's hard to memorize the formula of a finite geometric series. And that's where the power of deriving it comes in. Because you don't have to memorize it. In fact, I don't even memorize it. Sometimes it's the power of just deriving it and going from scratch to find it, right? And because this derivation is not like really hard. So it's important to actually know the derivation. So we start with Sn, and then how can we really create a formula? Well, the only thing we notice here is that each term after it is r times the previous term. So this motivates us to create a new series called r times Sn, right? And you'll figure out that this is the same as this is the same as this, and this term is the same as that. And so what we can do is we can subtract the second equation from the first equation to get r minus 1 Sn is equal to a0 r to the nth power minus a0, because only these two terms are left. And then rearrange for Sn, and then you will get this formula. So you could have either written this or this, both work. Right. For B would be infinite geometric series. So infinite assumes that the absolute value of r is less than 1. Let's think about this kind of intuitively, right? If we have an infinite geometric series where r is greater than 1, what would happen? Let's say r equals 1.5, or r equals 2 for simplicity's sake. And then we start at 1, right? And then we go to 2, 4, 8. And then one thing we figure out is that the terms just keep getting larger. They get larger. And so there's no way that it can converge. And because of that, there's no point in calculating an infinite geometric series when r is greater than 1, because it's just going to diverge. So the only purpose for infinite geometric series is that r is smaller than 1. And to do this, you just take the limit when n approaches infinity, and you end up getting a0 over 1 minus r. All right, now we're actually going to calculate the sum of two series. We're going to apply those formulas to actually calculate some sums. So the first one, we have 4 plus 6 plus 9 plus dot dot plus 729 over 16. Now, first of all, we need to find how many terms there are. And it turns out there are 7 terms. How do you find that quickly? You know that the common ratio r is equal to 3 over 2 because it's the next term divided by the first term, right? And so every time your number is going to lose a 2, right? 4 has 2 2s, 6 has only 1 2, 9 has 0 2s. And the next term has -1 2, which means that it has something over 2. And the next term will have over 4, over 8, and over 16. And this term is over 16, which means that this gives us a total of 7 terms. Again, you don't really need to do this. It's just a way to do these problems really quickly and efficiently. And with the terms, we just plug and chug with our formula, right? Over here, or actually, I use this one. And so, yeah, getting here is perfect, is full points. You don't have to go any further if you don't want to. And then for the next problem, this might not seem like a geometric formula, but it still is. Because we can pull the n out, right? And what I did here was I rewrote e to the n is equal to the e to the n minus 2 times e squared. And so after that, I just pull the n minus 2 out to get e over 3 to the n minus 2 times e squared. And then we get that our first term is going to be 3e, and the common ratio is e over 3. And with sum, and plugging in this formula and simplifying, we get that the final sum is 9e over 3 minus e. Yeah, and this is the first page, so please take some time to look over it and review any problems that that weren't that clear. All right. Second page. So again, now we're into the lands of the Maclaurin series. Now with this, I kind of want to review the idea of Maclaurin series. I think it's a really smart idea, right? So how do we know that a function f of x is the same as its polynomial expansion? How do we know that? Well, we take a look at one point. Let's say f of 0 and p of 0. And for them to be the same function, f of 0 has to equal p of 0, right? But that's not the only condition. There are infinite functions that have the same f of 0 and p of 0, right? There are so many functions like that. And so the next step is that f prime of 0 has to equal p prime of 0. And I think you see where we're getting at. F double prime also has to equal p double prime. And this continues indefinitely for any derivative of f and for any derivative of p. This is where Maclaurin comes in. And so in here, we want to find the Maclaurin series of ln 1 plus x. It's really the same idea. So we have okay, so in the first column, we want to list all the functions. In the second column, we want to evaluate the function at 0. And then for the third function, we want to find the coefficient for the polynomial expansion of ln 1 plus x. So for the very first line, for the first function, we just have ln 1 plus x. Because it's the same as this, we just copy that over. And then after we take the derivative, we have 1 over 1 plus x, which we can write as 1 plus x to the negative first power. And then this going over, right, we don't have to use quotient rule, we can just use power rule, and and chain rule or u sub if you want to do that. And then we get negative 1 over 1 plus x squared, 2 over 1 plus x cubed, and so on. I'm not going to go through the process of differentiating. Yeah, please review one of the earlier chapters if you need help with differentiation. And then when we evaluate the function at 0, this gives us ln 1, which is 0. This gives us 1 over 1 plus 0, which is 1. This gives us negative 1, 2, and so on. And then I kind of want to go back and revisit where this formula came from, right? So again, the key idea in Maclaurin series is that we want the kth derivative of f of 0 to be equal to the kth derivative of p of 0. But what is the kth derivative of p of 0, right? We know that p is a polynomial, so it's something like an x to the nth, and then there will be some k such that we have the coefficient ak and then x to the k. When we take the kth derivative, ultimately, this thing by the power rule, will become ak minus 1 times k, xk minus 1, and then kk minus 1, ak minus 2, xk minus 2. And then when we differentiated k times, we will ultimately get this coefficient multiplied by k factorial to be the kth derivative of p. And so that's where this formula comes from, right? And then the general form is just negative 1 to the n plus 1, 1 over times 1 over n. And because in here, k started at 0, so you want to do n plus 1. All right, after we do that, we can write the series for ln 1 plus x. And then, that's basically copying this down. If we have the individual coefficients, all you have to do is to add the x to the nth power on the top. And then we know interval of convergence is negative 1 to 1, inclusive of 1 and not inclusive of negative 1. And to prove that, and here I actually made a mistake, it should not be alternating series test, it should be ratio test. So what you would want to do is you'll want to look at x to the n plus 1 power. So if we were to do the ratio test, we would get this. So n plus 1 becomes n plus 2. And you want to divide by the original. And you want to take the absolute value of this. And ultimately, you want to take the limit as n approaches infinity to see if this is smaller than 1. So because this is absolute values, we can say goodbye to our negative 1s. And then what is left? Okay, so this should be an n, my bad. And then what we are left with is xn plus 1 over xn, which is just x. And again, so because the limit n approaches infinity, n plus 1 n is irrelevant. And so what this shows us is for the ratio test to work, this limit must be smaller than or equal to 1. So we know that this range is between negative 1 and 1, but we do not know the endpoints. So again, we have to test those endpoints, or those edge cases, as we call it. For x equals negative 1, right, it's basically it's basically negative 1 over n, so it's basically the harmonic series, but all the terms are negative. And keep in mind that this is not the alternating series. The alternating series switches sign, which means that it would do something like this, negative 1 to the nth power. But this is all negative, so it's the same thing as the harmonic series, and so this diverges. On the other hand, the other edge case, x equals 1, is the alternating harmonic series, so it converges. All right, I think, Problem 6. This is about the alternating series bound formula. And so let me just add a quick page to kind of illustrate that real quick. So when we have an alternating series, right, we have A1, A2, A3, A4, etc. And then A1 is positive, A1 is positive, A2 is negative, A3 is positive, A4 is negative, and so on, right? It keeps going back and forth. And because it goes back and forth, let's say this is the ultimate value. Let's say this is the final value from the whole sum, right? This is the actual value. In this case, this would be pi. So if a1 were to be positive, we would go over pi. But then a2 would bring us back under, a3 would bring us over, under, and so on. So what does the first dot represent? The first dot represents a1, or the sum after one term. The second dot represents the sum after two terms. Sum after three terms, sum after four terms, sum after five terms, 6 terms, 7 terms, etc. And then we would always go over, under, and approach pi. That's how the alternating series works. So how did we get from S1 to S2? We added by A2. How do we go from S2 to S3? We added by A3. S3 to S4, we added by A4. And we can repeat that process indefinitely, right? We just keep doing that. But one thing we want to notice is that the error between S1 and the actual value is certainly smaller than A2. And same idea for S2. The error between S2 and the actual value is certainly smaller than A3. And this actually applies for any S. Let's take a look at S6. This error is certainly smaller than A7. So S6 minus pi is certainly smaller than A7. And this is what gives us our alternating series error bound, right? Okay. And then with the alternating series bound, we know that Sn minus pi is smaller than an plus 1. And so in order for this to work, we need an plus 1 to be smaller than 1 over 1000, because we want to approximate pi with the accuracy of better than 0.001. And that's the only way Sn minus pi is smaller than 1 over 1000. So to do that, right, we plug in our expression, we plug in ak plus 1, and we keep doing that, and then we ultimately find out that we need 2,000 terms. And note that many people just stopped at 1,999. We actually end up needing 2,000 terms because k starts at 0. All right. Question 7. So in class, we just kind of went to the summary that sine x converges everywhere. But this wants us to prove that, right? And I think it's a really amazing proof because you actually get to see why sine x is converges everywhere. So when we want to find interval convergence, usually we use the ratio test, right? We check the limit as n approaches infinity of an plus 1 over an, and then we want to make sure that it is smaller than 1. So the limit actually simplifies to x squared over 2k plus 2, 2k plus 3, k approaches infinity, right? This one. And this is equal to 0 regardless of x, which shows that the interval convergence is everywhere, all real numbers. And yeah, I think this is a really amazing technique because it really justifies why something that we said is true. And proofs are nice, so yeah. All right, first page done. Let's move on to the next page. By the direct comparison test, show that the series diverges or converges. So if we have a series L that is 3 to the n over 2 to the n, this series will diverge because this is basically a geometric series with r equal to 3 over 2. And because 3 over 2 is greater than 1, this one diverges. But our actual series is greater than the new series, right? Because there is a plus 4 on the numerator. And because of this, our new series must also diverge, right? Because series L diverges and series S is greater than L, by direct comparison, we know series S also diverges. So that's a beautiful direct comparison problem. All right, now we want to express more complicated functions at infinite series. So if we have a function like this that's not 1 over 5, or that is not directly 1 over 5, e to the x, sine, cosine, ln, and tangent, inverse tangent, then we want to compose it so that it is 1 over 5. Right, so here we start with our e to the x, and then if we can do something to the function, we can also do something to its polynomial expression. So if we replace x with 2x, we can do the exact same over here. X becomes 2x, x squared becomes 2x, parentheses squared, and the same thing here. But we're not finished because we also have to multiply by an x. So 1 becomes x, 2x becomes 2x squared, 2x, parentheses squared becomes 4x cubed, and so on. Ultimately, this becomes our answer. Okay, next one, cosine x squared. So again, if we can do something to a function, we can always do it to the polynomial. So we're given cosine x as this, and then if we can change the x to an x squared over here, we can change all these x's to x squared over here too. All right. Problem 10. Sine x over x dx is a famously difficult integral to solve which has no closed form. And so, to kind of look at this integral, we want to create a polynomial expression that can approximate this value. All right. So first of all, we want to sketch a graph, and yeah, sometimes I know it can be hard sketching graphs, but the best way is just to plot points. And what I started with was I drew sine x on the top and x on the bottom. And then I looked at what would happen at each of these points. So at x equals 0, right, we are unclear of what will happen because both of these are at 0. But over here, sine x is at 1, and x is also at like pi over 2, right? So, but later, sine x always goes within the bounds of 0 plus 1, while y equals x goes upwards to positive infinity and downwards to negative infinity. So our function sine x over x is going to basically be very, very close to the x-axis. And then we can have our idea back to our squeeze theorem, where limit as x approaches 0 of sine x over x is equal to 1. So we would start at 1, and then it would just oscillate. But every time it gets smaller and smaller and smaller. Right? Every time it oscillates, it gets smaller and smaller. That's 10a. That's how you would sketch a graph. And then 10b. So the first thing we want to do is we want to just represent sine x as this polynomial expansion. And then again, if we can do something to the function, we can always do it to the derivative. So we can divide by x on both sides, giving us this. And then when we integrate it, right, all you have to do is, and then again, if we can do something to the function, we can always do it to its polynomial. So we can integrate both sides from 0 to pi. And so on the right-hand side, if we integrate that, we can use power rule, and that gives us this, right? Plugging in our limits, 0 and pi, we get this as our final answer. That's an amazing approximation of sine x over x, so kudos to Wolo. Alright, divergence, conditionally convergent, absolutely convergent. So this problem we actually did back here, right? It's just a direct comparison, and this diverges. This is conditionally convergent because it's an alternating series. However, the actual absolute value does not converge because it would be 1 over root 1, 1 over root 2, and then by p-test, this will diverge. So it is conditionally convergent. This is absolutely convergent because we can use the ratio test. And this gives us, ultimately, from the ratio test, the limit is 0. So this would be absolutely convergent, even if you were to take the absolute value. And similarly for this, for the last one, it's also absolutely convergent because we can use the p-test, p-series test. All right, last page. Find the sums of the series. So this requires some observation, but this, right, is basically e to the x. Because 1 plus x squared over 2 plus x to the n over n factorial, this is e to the x. This is just the definition of the polynomial expansion, Maclaurin series. And so because we're plugging in x equals 1 over 2 here, right, and I'll write that out again. Sorry for erasing it. We can plug x in over here. So we get e to the ln 2, which is equal to 2. Same idea for this. We know that sine x is equal to this. And so if we divide sine x by x, we get a series like this, which perfectly matches our series over here. And so in here, we're plugging in x equals pi over 2, and we get 1 over pi over 2, which is 2 over pi. All right. Problem 13. Okay, so in here what we want to do is we want to write the first 3 terms for f prime of x. And again, the same logic applies. If we can do something to the function, we can do something to its series, right? So if we can do something to its function, if we can take the derivative over here, we can also take the derivative over here. And just by using power rule, remember n is a constant, so we don't have to do chain rule over here. We get 2n x 2n minus 1 over n factorial. Right, I just wrote this, copied this for simplicity, and then you can take the derivative, and then you would get, yeah, and then you would get 2n times x 2n minus 1 over n factorial, and then n and n factorial, right, they kind of cancel, leaving us with this. So expressed as a summation notation, you just take the sum, and then you plug in the appropriate limits from 1 to infinity. All right, 14. So again, if we go back, we can use our formula that f3, that ak is equal to f to the k of 2 over k factorial. And so if we plug this in for 3, we get this expression, and then plug in our values, we end up with 7 over 2. And in this problem, I really want to highlight why that is true, right? If we take the third derivative right over here, or let's start by taking the first derivative. If we take the first derivative, the only term that really matters is the 3 over here, is the 3, let's say u equals x minus 2. We have 3u over here, and then the only thing that's going to matter is 3. If we take the second derivative, we have something like 5u squared over 2, and then once we take the derivative 2 times, we're going to get, first time we're going to get 5u and then 5. Third derivative, right? we have 7u cubed over 12, derivative once, that becomes 7 over 12 u squared times 3. And then this becomes 7 over 12 u squared times 3 times 2. And this is where the factorial comes from, right? Yeah, that's a really interesting way to understand it. All right. Problem 15. Approximate cosine 1/2 using S4 of 1/2, the fourth degree Taylor polynomial centered at 0. So again, we can always, again, that same idea. If we do something to the function, we can do something to its series. So cosine x, we know the series for this. And then cosine 1/2, we can just plug in 1/2 here. And then note that this is the fourth degree Taylor polynomial. So we only need the terms 1, this squared, and then this to the fourth power. We don't need 4 terms. And again, in the alternating series bound, right, we start with something bigger, and then we go smaller, and then we go smaller, and then we go bigger, and then we go smaller. So this error, right, the error at P4 is this, and it has to be smaller than this thing. But what is this thing? This thing is just the value of the 6th term. It's what you get from the 4th degree to the 6th degree. So it's just a6. And then you plug it in, and the error should be approximately this, or smaller than actually. All right, and this problem, the last problem, is a really interesting one because it deals with geometric series, although it doesn't really seem to. Right, so 1 over 1 minus 2x is really similar to a geometric series formula. So in this case, we can just let a0 be equal to 1 and r be equal to 2x. And so you would get an expression like this. And then this converges if and only if the absolute value of 2x is smaller than 1, because that's infinite geometric series. That's the rules. And here, I just want to go on a little bit of tangent. If and only if, what does that mean? That's not me trying to be cool. Okay, I might be aura farming here, but it's not just that. Right? The idea of if and only if is that if it converges, then this has to be true. But at the same time, if 2x is smaller than 1, we also know that it converges. In other words, this is biconditional, right? So that's something that's pretty cool to know. It's a chance for me to aura farm, but yeah, let's continue. So x has to be between negative 0.5 and 5. And in this case, it was nice. It didn't ask you to test the endpoints because all you need to do is find the center and radius. So center is 0, radius is 0.5. All right, I hope you had fun watching this video, and please ask me or Wolo or anyone if you have any more questions about this assessment. Yeah, I hope you're having fun in BC too, and yeah, thank you.